Today, we will proceed on our way to the proof of Topology theorem. We will take this lecture, next lecture, also the last lecture, and I hope that I would like to remind that on the last lecture, we have proved the following: that if we have a manifold, and it is not so important whether this manifold is, I would like to consider manifold with more function, and it is not so important this manifold can be closed, or it is possible that it has two boundary components, but one of them minimum of the function, and the second is maximum of the function, and all other values are in between, and we always suppose that all this guy is common, and no critical points on the function. So these are our usual assumptions. I don't want to step once more times, and the assertion which we can prove last time was that we can change our function. Our goal is not to study a function. Our goal is to study a manifold. So we will freely change function and change gradient like vector field, so that you obtain them easier and easier. And so we can change this function so that it becomes a self-indexing most function, which means that f of every critical, the value at every critical point p is equal to its index. So we have all points of index 0, 1, on value 0, all points of value 1, 1, on level 1, and so on. Moreover, whenever we want, we can move one of these points slightly. All points of the same index are on the same level, but whenever we want, we can again change slightly our function so that one of them becomes, say, below this level, or other slightly above this level, so that we have freedom to change them here. And next step is to study the case of critical points of whose indices differ by 1. So assume that we have a critical point P and a critical point Q such that their indices differ by 1. So here we have index lambda and Q is for index lambda plus 1. What happens then? Then, yes, the dimension of the whole manifold is m. And now we can consider some level set in between. Then this level set m contains two spheres. It contains right-hand sphere of P and left-hand sphere of Q. And dimensions of these spheres, well, right-hand sphere at P has dimension, right-hand disk has dimension n minus lambda, so sphere has dimension n minus lambda minus 1. Left-hand sphere at Q, disk has dimension lambda plus 1 since the index of Q is lambda plus 1. And so the dimension of sphere is lambda. So the sum of these, the dimension of the ambient manifold, of this level manifold, is n minus 1. So the sum of those two dimensions is exactly the dimension of this level set. And again, as we discussed on the previous lecture, we can change gradient flow, we can change gradient light vector field, so that to obtain that these two spheres are transverse to each other in M. They can be made transversal by an isotopy, and we can organize any isotopy by changing our gradient light vector field. So we may always assume that these two spheres are transversal. And then, since the sum of their dimensions is exactly the dimension of the ambient manifold, they intersect in a finite manifold. So this intersection finite. What else can we say? Another important thing is that we can assign a sign to every. The matter is that let us what I would like to be careful here. The matter is that it is natural to try to organize some sign by considering orientations, but the matter is that I do not want the whole manifold W. Maybe it is not oriented, so I don't want to use the orientation of the ambient manifold W. But actually, we do not need this orientation. The matter is that, okay, let us choose the following things. For every critical point, how our manifold W looks like in a neighborhood of a critical point. It looks like a standard. We have already proved that near a critical point, our function in appropriate coordinates is just standard quadratic function. So at point P, we have the following situation. We have lambda dimensional left-hand disk and n minus dimensional right hand disk. Right. And what we do, we choose one of the two orientations for the left hand. So here we choose and fix and orientation. Of course, every disk is orientable, so there is no problem to choose one of the two orientations for this. Now let us choose this orientation for every critical point. For every critical point, we have a disk of the corresponding dimension number, and we choose and fix all the orientations. Note that if W were oriented, then we automatically obtain orientation of right hand disk also. But I don't want to use the orientability of W. So we do not have any prescribed orientations of the right hand disk. Instead, for the right hand disk, we have so-called co-orientation. Co-orientation is orientation not of tangent bundle. Orientation is orientation of tangent bundle. But here we have orientation of normal bundle. The matter is that, look, normal bundle to the right hand disk is again trivial. Any bundle over the disk is trivial. But and so its orientation is given by its orientation at any one point. And its normal bundle at point C is exactly this left hand disk. So if we choose orientation for left hand disk, we immediately obtain co-orientation, that is orientation of a normal bundle to the right hand disk. So general situation is that left hand disks are oriented and right hand disks are co-oriented. Well, I already said last time, the matter is that this terminology goes back to Newman, which is one of the book lectures on topology, and the idea was that I don't know why, but Newman never used this intuition with K function. He never uses K, and he never draws pictures in this direction. He always rotates pictures. So the function is from the left to right, and one of them is on the right, and the other is on the left. So if you rotate, then it becomes natural now it is usual to draw pictures from invertible direction. But this terminology is still standard. Orientation means that normal bundle is oriented. Here it is not orientable and co-orientable. The matter is that it is oriented and co-oriented, so we have some prescribed orientation. We have chosen prescribed orientation here, and we automatically obtain prescribed orientation here. Well, this one is oriented and this one is co-oriented. And then what do we see? What do we see at an intersection? Consider an intersection point x of x is an intersection point of right hand sphere of P and left hand sphere of Q. What do we see here? First of all, write this left hand sphere of Q is just the boundary of left hand disk. So we automatically have orientation of it. uh, just induced by the orientation. The left hand is oriented, so we automatically obtain orientation of this. So this sphere is oriented. And what can we say about this sphere? Look, this when we say oriented, we must say where it is oriented. This one is oriented in the pole W. Well, but this means I put here Q. It's not I would like to say Q. But what can we say about right-hand sphere? Look, this is right-hand disk, and this boundary is right-hand sphere. Normal bundle of this sphere in M is exactly the restriction of the normal bundle of this disk in W. So this one is co-oriented in M. So now let us draw a picture in M. In M, here is a picture in M. We have this. We have this right-hand sphere at. Sorry, I'm interested in left-hand sphere. U and right-hand sphere is P. Sorry, right-hand sphere, and I have left-hand sphere in Q. And this left-hand sphere is oriented, so we have orientations in tangent bundle. In particular, if we have an intersection point, we have prescribed orientation of tangent space here. And for this yellow, for this right-hand sphere, we have co-orientation, so orientation of its normal one. And of course, at this point P, we have natural isomorphism between tangent space to this sphere and normal space to this sphere. They are transversal to each other, so we have isomorphism between them, and we may consider whether the orientation is agreed or not. So we get sine here. Sine of x is equal to plus or minus 1, depending on whether there is two orientations agreed or not. The orientations so yes, the picture is as follows. Once more, if we have two critical points of consecutive indices, W and W plus 1, then left-hand sphere and right-hand sphere for them, we may change gradient. We can assume by changing gradient like we can assume that they intersect transversely in M, and then we can assign signs to all their intersection points. And then it is natural to count the number, the algebraic number of intersection points with these signs. Not the total number, but the algebraic. Just like summing, take the sum of these signs. And let us denote it by this symbol. The algebraic sign, the algebraic sign, or the algebraic number. What the algebraic number of intersection points, of these intersection points, and let us, I have already said it last time, but what is an intersection point of the triangle here and that is just a geodetic, or not a geodetic, a trajectory of our radiant light field, which goes from Q to P. Well, there are two possible agreements whether we consider descending radiant light field or ascending. Actually, say in Miller's book, they are ascending. My intuition says that descending is more intuitive, but conceptually there is no difference. So actually, all this stuff allows us to assign a sign to every trajectory from Q. So for every trajectory, we assign either plus 1 or minus 1. And we just compute the number of all trajectories from Q1 to P with these numbers, with these signs. Yes? Well, actually, at this point, I must confess that actually I knew from the very beginning that at some point we will need some homology theory, which is not around homology theory. At this point, and starting from this point, we have to work with singular homology, cellular homology, and let us discuss what happens here from the viewpoint of cellular homology or singular homology, which is just I would like to remind you that we have already discussed that whenever we pass through a point of this lambda, from homology point of view, we attach a lambda dimensional cell. I would like to study at every point, I would like to study WA, which is all the part of the main W below the level. Yes. And when we pass through a critical point of index lambda, we attach a cell of dimension lambda from the homology point of view. And so, well, if we have, let us for a moment consider closed manifold. If we have a Morse function with, let us consider this self-index a Morse function. So we have several minima on the same level. This is level 0. We have several critical points of index 1 on the level 1. We have several critical points of level 2, and so on. Then, from homology point of view, what happens? When we pass, here we have empty space. Below level, which is smaller than 0, we of course have empty space. When we pass to level 0, we attach several zero cells. This means that from homology point of view, we just have finitely many points. Well, if I would like to consider WA after homology, then we can actually have finitely many disks, but after homology we have finitely many points. When we pass through cells of dimension 1, then we attach finitely many one cells, like that or like that. Further, we attach finitely many 2 cells, 3 cells, and so on. So we obtain a natural CW complex, and we know that the whole label W is homologically equivalent to this CW complex, which is obtained by cells in this way. But let us recall, actually, I would like to recall that we not only discussed that when we pass through a critical point, then a lambda cell is attached. But actually, we saw that it is exactly this lambda cell. It is exactly lambda cell of negative, in direction of negative squares. So, if we choose these orientations, it is exactly the same as to choose orientations of all cells. So, choosing the orientations of that term is exactly choosing orientations of all cells CW complex. And so, look, to every critical point P, we have the corresponding cell, let us denote it by sigma P. This is just a cell of dimension lambda, of dimension index of P. And we have CW complex constructed out of these cells. And all these cells are oriented since we fixed this orientation. So, of course, in a CW complex, we have incidence numbers of cells. For whenever we have a pair of cells of dimensions are lambda and lambda plus 1, we can consider the incidence number of the corresponding cells. And a good exercise, I will not do it explicitly. The matter is that actually, of course, it is not possible to include in this course anything about CW complexes. And in a sense, I must assume that you know all this theory, but I cannot prove it carefully without saying a lot about CW complexes, but I have no time. So this is a good exercise that the corresponding incidence number of cells is exactly that number. This is exactly that. It is not very hard exercise, but it requires something complex, but not very much. Actually, this is actually a useful exercise. Yeah, here we of course the incidence number there is only if dimensions differ by 1. So again, exactly in the same situation. The dimension of the cell is always index of point. So here we have this number whenever index of Q is 1 greater than index of Q. And here we have this number whenever index of Q. And in all these situations,
если мы возьмем тут не лямбда, лямбда или лямбда, лямбда плюс 2, то мы тоже делаем так, чтобы не пересекались.
No, if we have, thank you very much. If we have lambda dimensional and lambda plus 2 dimensional, then first of all, we do not. Well, let us discuss this in more detail. What do we see if we take lambda dimensional and lambda plus 2 dimensional? Two critical points of this say lambda plus 2 or lambda plus 3 and so on. First of all, we actually do not see there is no level where we see simultaneously right hand sphere for P and then left hand sphere for PR. The matter is that this right hand sphere is a good object until we meet points of the next critical point. When we meet next critical point, then some trajectories from P finish there. And further, we do not see a disk. We actually see how this disk is obtained, how this say right-hand disk is obtained. We start from point P, and we consider all trajectories outcoming from P. Sorry, for these are trajectories for descending plane, like if we for descending, these are trajectories entering. It doesn't matter. We consider all these trajectories, and this is disk. Locally, this is disk, and hence further. But assume that we have met some critical point Q. Then there is no trajectory. So we have something like that. It is this, but then it is some disk with poles made by this by these two poles. So we have something difficult here. So if we consider level here, then the right-hand sphere of P is not a sphere, it's something more big. But if we consider level beyond, below Q, then left-hand sphere of R is not a sphere. So there is no level where simultaneously both spheres. But even if such level exists, even if such say we may assume that there are no critical points of index lambda plus 1. Then no problem. Then on some intermediate level we have these spheres. But the sum of dimensions is not n minus 1, but now it is n. So these two spheres, we cannot make them disjoint. Moreover, they typically intersect by one-dimensional submanifold. And so we have infinitely many trajectories from one point to another. So typically we have infinitely many trajectories from a point to another point if the difference in indices is greater than 1. And the same for CW complex. If you attach say 4 cells to sphere, then it can be attached very non-trivially, and it is not just described by one number. Generally. The case of two consecutive indices is the simplest one, and it is nice that we can work on with it. If just very good, we can work on it. Well, but what can we say? An important thing is that homology of this complex can be obtained by cellular chain complex. So how to compute homology? Usually homology, cellular homology of CW. We just need to consider chain groups. Chain groups. We can consider this is cellular chain group of X. And this means that this is just a free abelian group generated by lambda dimensional cells. Free. With orientation, we have free abelian group generated by the cells. But and of course we have differential. Which just is given by as usual the sum of these cells with corresponding and we know that standard theorem about cellular homology that homology of these complex is exactly singular homology of algebraic homology governed by is the same is standard homology of X with Z. This is standard situation. This is for arbitrary CW. But in our case, the nice thing is that we can describe these groups and these differentials without saying the word about CW. We see all these just on the side of Morse function. Namely, we should consider that C gamma is just free abelian group generated by critical points of this gamma. And free. This is the same, we have already proved. Free abelian group generated by critical points of this gamma. And differentials and differential is given by this formula. Well, yes. Just I write P and Q instead of sigma P and sigma Q. So, look, a priori, if I write down this formula, it is not obvious at all that the square is 0. But it follows immediately since this is the same differential as here, and we know that the square is 0 for any CW. A priori, it is not obvious here. But now, we can proceed as follows. If we have this manifold W, and we are going to compute its homology, then assume that we have this self-indexed Morse function, and we have gradient-like vector field such that all these pairs of spheres are transverse to each other. Then we just can write down this chain complex as follows. Each C lambda is just a free abelian group generated by critical points. And incidence coefficients is number of trajectories with signs, algebraic number of trajectories, and we write down this complex. And we know that the homology of W is exactly algebraic homology of this complex. This is a very important, not very fast, but important proposition. One more thing about this. We are interested the viewpoint of H topology theory, we are interested from the situation when let me B and B prime. When we have two boundary components, W is not closed, they also need this. Yes, when we have as I described at the beginning, minimum here, global maximum here, without critical points on the boundary, and we have these two components, such components. And what happens in this case? In this case, everything, all these things can be repeated, but we must always start with B rather than with M. And this means that we have the same conclusion, but for homology. Look, they play different roles. The matter is that this comparison between manifold and CW complex is valid for any part of this manifold below. So any part is homotopy equivalent to corresponding subcomplex. So the prime doesn't affect both. If we get a boundary only on the above, then no problem. But if we have below, then the matter is that these cells are attached to sometimes attached to this B. Okay, that's what we need about. And next, general strategy is as follows. Whenever we have, as in H topology theorem, we have this H, assume that this is H topology. We choose some self-interested Morse function. And now we would like to simplify this function. Simplifying means that we would like to decrease the number of points. If we achieve zero, so there are no critical points, then of course we need to see that this is a zero. So our goal is to decrease the number of critical points, and so our goal is to obtain some installation of critical points. In some cases, we would like to cancel a pair of critical points. And now we are starting by proving, we will start on this lecture, we prove Taylor installation theories. But when we can cancel a pair of what does it mean cancel a pair of a pair of critical points which we would like to cancel will always be of indices which differ by one. So assume that we have a pair of points of indices down and down plus one. Then we can always organize, we can move these points slightly below this level, and this one slightly above this level. And why we need this? We may achieve that our manifold, there are two level sets such that between these two levels we have only these two critical points. So let us move this P slightly above and cut all other critical points in this lambda, and move this Q slightly below and cut all other. So we have the situation which we want to study is as follows. We have such a component. So now from this I pass to this one, but again I would like to consider to denote it by P prime the boundary components W is the total manifold, but now it is a piece of it. And here we have only two critical points. In between of these two levels, we have only two critical points of indices lambda and lambda plus 1. And our goal is to, under some conditions, of course, it's not always possible, but under some conditions, our goal is to change function here so that it doesn't have critical points at all. So the initial function has two critical points, and we would like to change it so that the resulting function will not have critical points, and it will agree with f on the boundary. This is our goal, and there are several situations when we can cancel pair points. And today we will start from the simplest one. And the simplest one is as follows. Assume that we will always assume that, as usual, that these two spheres, left-hand sphere of E and right-hand sphere of E and left-hand sphere of Q, are transversal to each other. And so we can use this appropriate number. But assume that we have exactly one projected from Q to E. Not just, now I want to say not about algebraic number, but only one project. Yeah. This is the assumption. And then it turns out that in this situation we always can cancel this. So this is our theory. So theory. Assume that we have this, it is called triad, WB prime, and more function to R. I will always assume that it has global minimum E, global maximum prime, and no points on the boundary. So PQ are the only two critical points of indices lambda and lambda plus 1 respectively. And also we assume that right-hand sphere of P is transversal to left-hand sphere of Q, and they have a unique intersection point. So which is exactly the same as to say that there is a unique trajectory. Yes, well, of course, we have this f, and we have a gradient like vector. And this is the same as to say that there exists exactly one trajectory of C from Q to P. From Q to P in my descendant, agreement from Q to P in descendant. Then we can change the pair F of C to some pair F tilde and C tilde, so that F tilde and C tilde coincide with F C near boundary. Near master boundary, and C tilde is graded by vector T for F tilde, and F tilde has no weight. F tilde has no weight. And C tilde is graded by for F. So our goal for today. So we can cancel this pair. Well, how to prove theorems like that? And look, when we studied our answer, well, first of all, the first thing I want to say that this theorem is not easy, and the reason why it is not easy is that it is not local. Look, actually, our we can consider small neighborhood of our trajectory. So we have this trajectory T, and we can consider small neighborhood of our trajectory. And in fact, we will change a function and the vector field only in this small neighborhood. And from the first glance, you may think that actually this is a local theory, something in the neighborhood of trajectory. But this theorem conceptually, essentially, means that there is no other trajectory like that. It may happen that there is another trajectory of T, which is not close to T, which goes somewhere far from T. So if we study our function and vector only in the neighborhood of T, then we just do not see that we cannot detect whether we have such another trajectory or not. But if we have such a trajectory, then theorem is just not true. So we never have cancelled the pair of critical points, pair of critical points. That is very easy. Reason why we can just very naive example. Assume that V is just empty. I would like to like that here. I would like to have I would like to have well, I try to draw you zero. Yes, I would like to draw you two-dimensional example. So this is just just such a cell. Well, let's draw a torus and cut the upper half. This is prime. These are two sockets. This is lambda is equal to 0. Q is equal to Q is a point of unit 1. And actually, in this equation, we have two trajectories. And of course, we cannot cancel such a pair of critical points. Why we cannot cancel it? If we could cancel it, then we just obtain a signature, but even prime are not become So this condition that we have exactly one also is a crucial condition. You cannot avoid it at all. And this condition is not local. You do not see it in the neighborhood of our T. So though all our change function will be in the neighborhood of T, we must use the non-existence of such condition. And this is why we see buffer. Well, not now, but okay. Now let us start. But our first step will be local. Our first step will be some kind of Morse lemma. What Morse lemma says? Morse lemma says that in a neighborhood of point, we can choose a coordinate system so that the situation is very static. So that our Morse function is just quadratic function. Now our goal is to do the same thing in a neighborhood of a trajectory. So I would like a small neighborhood of this trajectory is of course topologically existing. So we can choose a small neighborhood which is existing. And our goal is to introduce coordinates in a small neighborhood so that the situation is very static. And first of all, let us describe what is a static situation. I would like to have. So I would like to introduce coordinate some neighborhood. Our goal. We have coordinates in the neighborhood. These coordinates will be x1, xn. And I would like to have the following situation. First of all, P in these coordinates is just the origin. U is 1, 0. And T is just segment, straight segment. In these coordinates, it is one straight segment. So the situation is like that. P, Q, I would like the coordinates situation is like that. This is T. This is our x1. And actually, for me, it is not. The main idea is that I do not want to consider function f almost. What I want to work with is very likely. So the thing for me is more important than and so I would like that is very likely. Yes, very standard form. I would like to recall that what is a gradient vector field in my descendant agreement. It is a vector field such that this derivative is negative of critical points, and at each critical point, our field is just standard. In a critical point, we coordinate table as a Morse lemma. We would like to have C equals to x1, x lambda minus x lambda plus 1 minus xn in these coordinates in small neighborhood. And here I would like to say how C should behave near the whole trajectory. And yes, So I would like that, I will explain what is V. V is a function like that. So I would like that C is written by very explicit formula. This is true in a neighborhood of trajectory. Very explicit formula like that, where V is the function as follows. This function is x near the origin. It is 1 minus x near point 1. And it is positive and smooth. Look, what happens here? Assume for a moment that C is of this form. Well, what do we see? Sorry for what do we see near P? Near P we have just minus x1 here. And so I have lambda positive and all other neighborhood negative. Yes, I would like that our function f, is so I would like also that this coordinate neighborhood near P it is just standard Morse neighborhood. Standard neighborhood from Morse neighborhood. So near P, but here I have reordered coordinates, but this was not match. So minuses are equivalent minus squares range from 2 to down plus 1 and all other classes. So this is a situation near P. So near P we have standard situation from Morse lemma. Function is like that, and vector field is just minus x1 here. This is standard situation from Morse lemma. This is near P. What is near Q? Near Q, we also would like that this is a standard coordinates from Morse lemma, but with this shift by 1. So near Q, we would like that f equals to f of Q minus x1 minus 1 squared. So we have lambda plus 1. Q is point of view lambda plus 1. We would like to have here lambda plus 1 negative squared, but the first of them is x1 minus 1, not 1, since we have this shift. And again, near Q, we have here y minus, we have here x1 minus 1. And this is again our standard vector field in Morse lemma. So, proposition is that there exist coordinates in the neighborhood, of the whole trajectory, such that our gradient like vector field is like that in the whole neighborhood. But in this form, the proposition seems to be not true. Correct proposition is as follows: that we can choose gradient like vector field, maybe different one, maybe not as it was initially. So we can change gradient like vector field, but for the same function. In a neighborhood of T, so proposition is that we can change C in a neighborhood of T and organize such coordinates, maybe in small neighborhood and choose coordinates in a smaller neighborhood of P, so that all these things are true. That's our claim. This lemma is more or less it is very technical. So just there are plenty of conditions. But when we organize like that, then it will be very easy to work with it. When our function is so standard, then it's rather easy to work with it. But well, now let us prove this lemma. Actually, it is not so hard. It's not so hard. And well, actually, the main idea here the main idea is here is as follows: that look, let us consider some point here. Some point here. Any point. This is our maybe it is better to draw it here. Let us consider this trajectory from Q to pi. Yes. And consider any point in the field. It is on some level. What do we see on this level? We see here a right-hand side, a right-hand sphere of Q of P, yes, and a left-hand sphere of Q. And we know that they are transversal to each other. Transversal to each other, and their dimension is the total sum of dimensions is just the dimension of this level. One important lemma which I would like to give as an exercise, but it is really very standard and rather easy. Lemma. Assume that we have just a local situation. Find it out what functions and anything like that. We have two submanifolds of a manifold of dimension R plus. And we have transversal point of intersection. This will be R and S. And we would like to consider, assume that R and S are transversal to each other. Are transversal to each other. And assume that we have got well, X is a point of intersection. Then locally this intersection is like exactly as the intersection of standard equilibrium. So I claim that if I So we have got such situation. This is M, and locally we have these two R and S. And claim is that we have local diffeomorphism, so diffeomorphism of some neighborhood of point X just to a neighborhood of the origin in standard within space, such that R and S go to the standard Euclidean subspaces spanned by first and last base. So this is an exercise. Only what does it mean? Well, what does it mean? This means that we can locally. I would like to apply this means that locally we can choose here a neighborhood such that there exist local coordinates, so that these two submanifolds are just coordinate subsets. So what does it mean? This means that near this point, we can choose coordinates. Our global goal is to choose coordinates in this neighborhood. But now let us start from this point. We can choose coordinates, say y1, yn, so that first of all, this level set is exactly, let it be just by 1/2. This level set is exactly y1 equals to 1/2. Well, and those two spheres are given. Okay, now I would like to compute this blue sphere. Blue one is left hand side, left hand sphere of Q, and I would like it to be the coordinate subspace spanned by coordinates y2, y lambda plus 1. Yes. And right hand sphere is spanned by y lambda plus 2, y. So we have this standard coordinate situation near this point. Now, I would like to proceed as follows. The next piece is better not to be right. But so let us make a break and then Well, let's proceed. I would like to draw a picture at larger scale here. And explain my local goal. Well, we have this trajectory from E. We have this right-hand sphere for E, but this right-hand sphere for E comes from a right-hand disk. So actually, we have here such right-hand disk. We have projectors which come in E. So we have such a right-hand disk. I would like to consider only part of this right-hand disk, which is in a small neighborhood because it goes in all direction. But just for me, it is important that there is such part which goes and also, this disk has dimension n minus down. The total dimension down is right-hand disk. This dimension n minus down. We have left-hand disk, which behaves like
Сейчас зафиксировали в ответственности точки.
Yes, I will do it. We have this left at least. Actually, this right hand disk it also goes further, but I don't want to draw it. Yes? I want to draw it only up to here. I can extend this right hand disk whenever I want, but I want to extend it only up to here. And similarly for left hand disk. And in fact, let us do slightly more. Let's extend it slightly. Actually, this picture, which was on 1/2, one can easily organize the same neo. So what do we see here? Here. I have already good coordinates. This is point neo 1/2. And neo 1/2, I have a nice coordinate system. Called y1, y2. Up to now, this is coordinate system just with the following properties. That first of all, y1 is can be chosen for a level set of. So I can say that function is y1 equals to const. These are level sets. So y1 equals 1/2. I recall that we started constructing this system by considering a level set. We choose this system so that y1 equals 1/2 is this level set. And then inside this level set, we have these two transversals. And it is not hard to organize that near this level set, y1 equals constant, these are level sets of are level sets. All these things are local. And also, I claim that this yellow disk is given by, it is spanned by coordinates y lambda plus 2 y n. And y1, of course. So this intersection is spanned by lambda. So this yellow is given by equations y2 y lambda plus 1 equals 0. All is near this point. And this blue is given by equations y lambda 2. So locally, this is what do I want? I want to extend this coordinate system to the left, so that this assertion about yellow disk is interesting for me only on the left. I don't want to study how yellow disk behaves on the right. But on the left, I would like this. I want this to be true in all points here, in all this range from 0 to 1/2 and slightly more. Level disk near the first part, let T1 is T1 is the first half, and T2 is the second half. Near T1. I don't want this to be true near T1. I'm not interested in blue. I would like this to be true over T1 too, but about level sets, but not completely. The matter is that at P, I would like to arrive at standard Morse, standard coordinate system from Morse level. What does it mean? This means that near P, I would like to have these coordinates y1, yn near P. I would like f to be f of P plus y1 squared minus y2 squared. So near P, I would like to write to this function. Of course, for y1 response is not level set to this function. But what I want that they are level sets here, but I would like that all everywhere here, y1 equals const are tangent to level sets of f. So they are tangent spaces next time. So level sets are, in a sense, are total to level sets of f. That is true here. Look, what happens here? In fact, I claim that it is not hard to organize the whole thing. Look, let us start with standard coordinate system near P. Near P, I have a standard coordinate system so that this disk is exactly spanned by necklace. This disk is given by this equation. Near P, I have standard coordinate system from Morse function, and this coordinate just with renumbered twice. And in this coordinate system, of course, the disk is spanned by this equation. That the right disk in a standard Morse neighborhood is valid given by this equation. Это разные. Здесь разные. Y's here and Y's here are different, but I want to stand the one to come. This will not be completely true, but let's rename coordinates which are here. Let they be. Maybe to avoid very technical, and here we see that in this neighborhood, of course, our coordinate, our right is given by equation x2 x number plus 1 equals 0. Right? So, in fact, how to extend these coordinates along it is not hard to well, it's very easy to imagine, very hard to explain. I'm sorry. The idea is that you would like to consider First of all, near this T1, let us say this important. Near this T1, at every point here, I have tangent space to level set of F. Tangent space. This is for dimension 1. And this tangent space is transversal to T. So this is tangent space to level set of F. And of course, I can, using standard partition of 1, I can easily endow this thing with remaining net. So the tangent space is orthogonal. Trajectory. So I can organize that this level set is orthogonal. Then, also, I would like to consider for each such level set, I would like to consider its intersection with our disk, our lecture disk. It is again orthogonal to this projector, and in this intersection, I would like to choose basis of tangent vector, orthonormal basis of tangent vector. Here, I would like to start with which basis is in P. This basis is what is the basis of tangent vectors of here in the standard table. In the standard table, this is just basis E2 E lambda plus 1. Oh, sorry. Vice versa. E lambda plus 2 E lambda. These are tangent vectors orthogonal to and I would like, and here I also have tangent vectors which are d over d lambda plus 1, d over d minus. Also standard. Here these i's are d over d x. But just changing, I would like to extend these through this basis along segments so that they agree. It is possible if and only if they have the same orientation. But this can be easily organized just by reversing one of these coordinates. I have freedom to reverse x lambda. So it is no problem to organize that these two bases here and here have orientations which agree to each other. So I can choose compatible bases in all these intersections. And then, in a standard way, using exponential math, I can organize the required coordinate system so that these first coordinate bases are so that these chosen bases are always d over d lambda plus 1, d over d over d. So this is I prefer to do this as an exercise to do it very explicitly. It is rather technical, but not hard at all. So once we have bases which agree to each other, we can organize such coordinates. So actually, I prove a very easy thing. If we have a disk, which proceeds along some curve, then we can organize the coordinate system so that disk is given by several coordinates equal to 0. And this curve is just a coordinate line. So this is not true. No. This is not hard to organize such a coordinate system. It would be hard if I want to consider two disks, but I don't. Just one. But very similarly here, I can follow along this blue disk, and so I can in total, I arrive to some coordinate system. Now I will. It was x's, it was y's, but now let it be x. I would like to describe what we know about these coordinates. So I claim that up to now we have coordinate system that be x. Well, so we have coordinates x1, xm in a neighborhood of t, such that first t is just a segment of coordinate line x1. This segment like n times. Second, at every point, second, I don't want to write down once more. Near P and near Q, these are standard coordinate system for most precise sets here. Third, at every point of T, every point of T, we have that if we consider tangent space for the point S, if we consider tangent space at S to the corresponding level set, then it coincides with space spanned by all coordinates. So it is a factor. And fourth, at every point of first kind, so near T1, T1 is the first half. We know that near T1, right hand disk of T is given by sorry, there x x2 equals x down to 1 equals 0. And I near C2 left hand Q is given by x lambda 2 equals n equals 0. This is what we could achieve. Now let us understand that this is required. Why? Why? Now, let us consider this particular vector field. We had some initial now let us slightly change notation. We have some initial gradient like vector field C. I don't want to consider it. I would like to consider this particular vector field, which is given by this precise formula in this small neighborhood. What can we say about this vector field? First of all, it is gradient line. One. The derivative of since because of this property 3, the derivative along eta of the function f depends only on this first code. Yes. And hence it is positive, negative as required. So well, it is negative in the field. No? So this explanation doesn't say us why f is graded like here. But here it coincides with the standard in this neighborhood. It coincides with standard graded like vector fields from most length. So in this neighborhood, you know that it is graded like since it coincides with prescribed vector fields. But in between, it is just because we have correct sign or required sign because V is stated positive, so this coordinate is stated negative, and this coordinate is exactly the derivative of. So this vector field is gradient line. Of course, when we have two gradient line vector fields, we have initial gradient line vector field, and we have new gradient line vector field, but defined only on the neighborhood of T. Then we can easily organize them in one gradient line vector field, just using partition of unity. So we can consider here some neighborhood. We can choose function rho u, which is 0 outside u, which is 1 in a small neighborhood. Well, here it is 1, and here it is 0. And then I can write down vector field rho u times eta plus 1 minus rho u times c. This will be a new gradient line vector field. Look, in a neighborhood of T, this vector field coincides with eta. So it is gradient line as we discussed. Far from T, this gradient line, why it is gradient line? Because this one is gradient line and this one is gradient line, and we have their combination with positive coefficients. So of course the derivative has the same sign. So we know that this is gradient line, and it coincides with eta, with the prescribed vector field near our trajectory. What is the hardest thing? Why I should consider all these pieces? Actually, in our proposition, we say nothing about this. We just don't worry about them. Why we need all this? Because if we just consider this vector field, the question is we change our gradient line vector field. And maybe now there are several changes. We knew for initial vector field that there was exactly one trajectory from Q to P. But we have changed our vector field. And we need to check that we still have exactly one vector field. Exactly one trajectory from Q to P. And why it is called so, this is the crucial step. Very important step that we need to check, to check that we still have a unique, exactly one trajectory from Q to P. And the matter is that, look, our vector field eta is organized so that it is tangent up to in the neighborhood of T2, it is tangent to this blue disk. Just this blue disk coordinate is given by this blue disk is given by these coordinates. Well, and this particular vector field is of course tangent. C is also tangent by definition. So this means that all trajectories of U vector field up to this level of F go inside the same blue disk. All trajectories, the matrix eta and C are tangent to this disk. Hence, all trajectories here go inside the disk. So U right hand disk, U left hand disk of Q is contained in the whole. And in fact, concept. Though it is not important. Similarly, right hand disk of P up to this value of F is contained in this yellow. And so, but now at this level, yes, we know that the whole spheres have a unique intersection. So we can hence use that spheres of Q and right hand sphere of P exactly at this level have a unique intersection. So we have a unique. Well, so we have proved this proposition. I'm sorry, it was rather technical. I proved it differently to what is saying in lecture of H algorithm. You may also prove there. There is also a nice proof. It seems to me that this one is slightly easier, but it depends on what is better for you. Both are technical. Okay, so what we achieved? We have achieved that our vector field is standard in an neighborhood of T. And this was local part. Actually, in this, here we never used, almost not used that there are no other trajectories. But now I would like to use it very closely. And now let us go to the global situation. So let us consider this the whole situation. We have P prime, we have here, we have the whole W and Morse function F, gradient like vector field C. Now I expected the resultant vector gradient like vector field. Now let it be C. So locally given by this formula, but globally we just know and we have this unique trajectory, only two critical points and unique trajectory on them. What and we have this neighborhood U. U is neighborhood in which all this is true. So in a small neighborhood we have this nice coordinates. But U is a neighborhood in which we have these nice coordinates. Now we are starting global analysis. Now next claim, next proposition is as follows. We are going to study trajectories of our related light vector field. How can these trajectories work? First of all, there is one very special trajectory. There are trajectories that start. How a trajectory can start? It can start either in the prime or in one of the a trajectory can start either in a critical point or in the upper. So there are trajectories which start here, and similarly, trajectory can finish either in B or in one of critical points. So all combinations are possible. There can be trajectories which start at V prime and finish at V. There can be trajectories which start, say, in V prime and finish in Q. There can be trajectories which start in prime and finish in V. Well, and so on. But of course, start in Q and finish in V, all combinations. But what is impossible? It is not possible to start at V and finish at Q. It is not possible to finish above. And there is only one trajectory which starts at Q and finishes. This is possible. So proposition is that there exists a smaller neighborhood, so such that U is contained, U prime is contained in U and contains our trajectory. So I would like to consider here a smaller neighborhood. With the following property, such that the property is as follows. Assume that a trajectory starts in U prime and after some time leaves U. Then it can return to U prime. This is property which is required. So such that if a trajectory, when I say a trajectory, I always mean a trajectory. If a trajectory starts in U prime and then leaves U, then it never comes back to U prime. Never returns back to U prime. So the claim is that such there is a neighborhood which is by this property. Let us try to prove this. The proof is non-constructive. Actually, assume that we assume that this is not true. That no, you can take arbitrary small neighborhoods of T, but none of them satisfy this problem. Let us take smaller and smaller and smaller neighborhoods, sequence of neighborhoods which we can introduce some method in there. And we can take smaller and smaller and smaller neighborhoods which approach T. And assume that for each of such inputs, we have bad trajectory which behaves exactly as written here. So this trajectory behaves like that. It starts inside point, which is close to it sometimes goes out of view and then it returns to the prime. So for all closer and closer and closer to t, but we have this trajectory. So we have such bad trajectory. So what is this trajectory like? It starts near t, it sometimes go out of u, and then it returns near t once again. Let us call, we have sequence of such trajectories, so that these and these points are closer and closer and closer to t. So let us consider this sequence and let us denote this point by rk, this by sk, and this by tk. And our this is the sequence of trajectories now, okay? And we know that distance from sk to t, from rk to t, tends to 0, and distance from tk to t also tends to 0, sk goes to 0. But now, look, first of all, t is compact. So, in fact, the sequence of RTs is a conversion subsequence. Then we can choose the conversion subsequence among these. And here, points are on T. And then we can also choose a conversion subsequence of S keys, set is also common. And moreover, the whole W without U, all S keys are out of U, and this one is common, since U is over. So, what we can assume that all these three sequences have limits, and limit of R and limit of T are in T capital, and limit of S is somewhere here. So, we may assume that let us so we may assume that there exist limits of sk, of rk, and of tk, and this limit of sk is s. This limit of rk. Well, I have already known. This limit, for me, it is important that, actually, for me, the most important thing is the limit of sk. And I know that it is out of u. It is somewhere here. And now, look how the trajectory from through S can be. What are they? For the trajectory from S through S. There is a unique trajectory through S. But what can we see? It starts either on prime or in U or in V. And also it finishes either in V or at P or at Q. But what we for sure we know that this trajectory is not T, because S is not in T. So assert, I claim that this trajectory either starts in B prime or futures at B. It is completely impossible that both start and finish are fused. Because there is only one trajectory with this property, and this is T. So we know that trajectory through S either starts at B prime or finishes at B. Maybe both. We have symmetry, of course, we can reverse our time. So these two situations are similar to each other. And let us assume, just for simplicity, let us use the first one. It doesn't matter for both situations. So the trajectory through S behaves like that. It starts at B prime and it goes to S. Well, so in a neighborhood of this trajectory, there are no critical points. Hence, if we consider points which are, hence we have, if there are no critical points, we have this continuous dependence of the trajectory from initial conditions. So if points are close to S, then trajectory, we have close trajectories here. Yeah, trajectories from next time from this point are close to this one. So they are far from T. So we arrive at interpretation. Because in this neighborhood we have plenty of this space. Space. And we know that for each of them, trajectory in negative direction approaches T. Turns out so I just want to say that it is completely logical that if there is another trajectory between Q and P, then this proposition is of course not true. If there is such another trajectory, then we can start arbitrarily close to P, and arrive arbitrarily close to Q, and in between we are far from P. So this is exactly at this point we use that there are no other trajectories. If there are no other trajectories, then we'll take this proposition. Well, now we are ready to change our gradient line vector so that to obtain that it has no more our C has two I would like to change the line vector. I will change it only in this small problem. Well, how will we change it? In this small group prime where we change our gradient line vector field, we are sure that our function is like that, and that our vector field is given by this precise form. Well, what I want here to choose function like that, which can say this one is B, and then like it is B function, which behaves like that. Just always have. But it has time size with B. I would like that of course, it coincides with V. Here we have some minus epsilon and 1 plus epsilon. Well, and I would like to say that, well, this what I want about these epsilons. I want that if we are epsilon close, let us introduce in these U primes just standard Euclidean metric. So just some squares. Let us introduce standard Euclidean metric in this document. Yes. And I would like to say that I would like to choose epsilon small enough so that epsilon neighborhood of T is contained in U prime. Let us choose small enough epsilon. Like that, since U prime is a of course we get T is small. And then I choose this function so that it coincides up to minus epsilon starting from 1 plus epsilon. And now let this U function be double. We have this B and we have this double. Now I would like to choose U function and U vector which behaves like that. It is one more thing. Of course, I would like to have this standard function rho. I would like to have function rho. Rho is function of W, which is 0 outside the prime, which is 1 near T, and which is close to T. So it is 1 near T and 0 outside the prime. Of course, we can analyze such. Then, as usual, just I just want to write down theta. I write down theta in our coordinate neighborhood. Outside, it coincides with in coordinate neighborhood, we have the following. We change only first coordinate. We would like just change it from V to W depending on this rho. So minus, we would like it to be V, we would like it to be S, let's say, outside the prime. So we are going to write here 1 minus rho X, yes, times V x1 minus rho of X times double of X prime. The standard form of combination. And all other coordinates are exactly like that. Well, what do we see? We see and C theta equals C of prime. We obtain the U vector theta. What do we know? We know for sure that it is never 0. Never is equal to 0. Indeed, C has no zeros except for P and Q, so it has no zeros outside U prime. But inside U prime, well, inside U prime, what can you say? That here we, well, sorry. Well, it is not correct like that. Let us do it correct. The matter, we should be careful to be sure that there are no zeros. For that, I would like to do it not in this way, but the function rho. I would like to have function rho, which is only functions of x to x n, independent on this one. And which behaves like that. It is 1 near the origin. It is 0 outside this epsilon. 0. And this thing that is still well defined. The matter is that we can, if we go far from t, then either we go far from t in x2 itself, or we go far from t in x1. If we go far from t in x1, then these guys just cancel. It doesn't matter which are the conditions. If we are going far from t by x2 xn, then this definition becomes so this CT is well defined. But now let us prove that it has no zeros. If 0 occurs, then the 0 can be only in U prime. Outside U prime we have C and it has no zeros. If assume that C theta equals 0 at some point x. Well, the matter is that, of course, these coordinates can be 0, yes? But it can be 0 only if this x2, xn is non-zero. Only if at least one of those coordinates is non-zero. If all x2, xn are 0, well, then this is 1, and we just have w, and w never takes 0. So either at least one of these coordinates is not 0, or the first coordinate is not 0. Well, so C theta doesn't take 0 value. But now, the most important part. The most important part is that C theta have all trajectories of C theta start and finish. This is the crucial thing. The matter is that our goal is not vector Q itself, but our goal is most function. And we would like to organize most function for which this C theta is really cycle. And the crucial assertion, the key assertion, is that now the lemma is that all trajectories of theta dot at B prime and finish at B. And it is not as easy as it seems to be. But now let us consider. First of all, first of all, we need to prove two assertions that all trajectories of CT that start at B prime, and all of them finish at B. And of course, these two assertions are completely similar to each other. So let us prove on one hand. Let us prove that all trajectories finish at B. So we are going to study a trajectory of B prime, or of CT. And I claim that we are interested only in those trajectories of CT that goes through U prime. Well, indeed, if a trajectory starts somewhere here and never goes to U prime, then it is a trajectory of C. Of U prime, our CT has set C. But if a trajectory of C never goes to this neighborhood, then it arrives at C. No problem. Well, so we need only study those trajectories which at some moment of time are in U prime. Well, but then we can assume that at time zero they are in U prime. So we consider a trajectory gamma of theta such that gamma of 0 is in U prime. What do we need to prove? I claim that we need to prove that our trajectory leaves U. Look, if our trajectory we have T, we have U prime, and we have this larger neighborhood U. But in this larger neighborhood U, we still have this beautiful. If our trajectory starts somewhere near U prime and it leaves U, then starting from this point, it becomes a trajectory of T. Of U, we have a trajectory of T. But we know that it never returns back to U prime. If it returns back, then it again not a trajectory of T and it may be calculated. But we know by this proposition that if it were U prime and leave U, then actually starting from some point here, it is a trajectory of T. CT differs from C only in some neighborhood. So this is a trajectory of C, and hence it never goes back to this prime, and we are done. So we only need to prove that there exists T positive such that gamma T is not positive. And that's enough. Now let us just solve differential equation. When we are U, then our trajectory just solve this differential equation. What we see, we see that it is the following system of differential equations. The first equation is difficult. G over x1 and minus rho, and we cannot solve it explicitly. Well, but other equations are very easy. Here we have just 2 and x lambda plus 1 dt equals x lambda plus 1, and here vice versa becomes 0, it is minus. What do we see? How to solve the last all of these equations? These are just exponents. We have this exponential solution. Let's write it down here. So, yes, yes. In U we have this while until we are in U. Actually, we could even say that they are true in some large from the very beginning. We have this formula in some large use U. So they are for sure true in U and actually in some large. What can we write down? X2 of t equals x2 of 0 to the power of t. And similarly for all these. And x lambda 2 of t equals x lambda 2 of 0 e to the power minus t. And similarly for all. Yes. What happens? Assume that at least one of these coordinates, x2 of 0, x lambda plus 1 of 0, is non-zero. Yes. Assume that originally at least one of these coordinates is non-zero. Then we have growing exponent here. And of course our solution goes out. Just we have coordinates which grows it can have unbounded growth. It grows unboundedly. This is true until we are in U. But so we necessarily leave U. If we always stay in U, then x2 of t tends to infinity. It is impossible. Okay? But it is only if at least one of those coordinates is not zero. But now it may happen that all these coordinates with positive sides here, all of them are usually as U. Then we have no such easy reason why this trajectory is U. These exponents are decreasing. They decrease to 0. So these are identically zeros. So this means that x2 x lambda plus 1 of t are just identical zeros. And each of those coordinates tends to 0 as t grows, and tends to 0 very rapidly, just as I mentioned. And the only reason why we can leave is the first problem. So we need to study this first equation. But what can we say? The matter is that before studying this equation, let us look on all these are zeros. And on this tend to 0 very directly. This means that at some point we will get in this direction we will get into those small neighborhoods where our function rho is 1. So we definitely know that starting from some t0 from some amount of time, we have that this function rho over 2 itself. So we are not interested in the first. On this time from 0 to t0, anything may happen, we don't want to study this. If on this segment we leave u, then we are done. Assume that we are still in u after this time process. We are still in u, and starting from that time, rho is just 1. So starting from the time, we are solving this equation. Yes? That's nice. The matter is that I have already erased it, but the function w was strictly negative. Something like that. And since we are on a compound, then it is smaller than something like that. And hence, x1 decreases with speed at least delta. So, if I have time, it becomes arbitrarily small. So, we our information does not to revert to yeah. But just imagine that this W is just strictly negative and it is strictly negative in this sense that there is constant. And hence this is one just decreases until we get out of it. So that's all. Now we have new vector field Ct which has the following property that all that this new Ct is never is non-zero. This new Ct is non-zero on the whole W. And all trajectories go from prime to B. And hence, just we can, as we have already done, we can easily normalize this vector field so that this trajectory goes from B prime to B exactly type 1, and then this vector field provides the our manifold W with this. And so a Morse function, just projection onto this time axis, is Morse function, which is non-zero, which has no that's all. Besides, we have all our vector field Ct that of course coincides with C in hence we can also, if we want, we can analyze that our Morse function also has the initial Morse function in neighborhoods of B and B prime. So this was a rather technical piece of proof, and what we have managed to do. So once more, we prove that we always can cancel a pair of critical points of consecutive indices such that there exists exactly one uh, trajectory from one to another. And well, we have 5 more minutes. I will announce what will be next. And next will be the following wonderful theory, which is actually older than most theories, or older than all of them. This is a wonderful theory due to Whitney, and now it's called Whitney tree. And this, in this we will have some dimensional restriction. And this is exactly where the restriction of dimension is 5 comes in the what is this theorem is not about Morse functions, not about it is just about transversal intersections of some methods. So assume that our situation now today I will relate it and we will prove it next time. Suppose that we have two submanifolds. It's not so important, but yes, two submanifolds. Of course, as usual, everything is smooth. Two submanifolds of complementary dimension. Sum of dimensions is dimension of the manifold. And this R and S intersect transversally. So they are transversal to each other. Now we would like also that R is oriented. Yes, so they intersect if everything is common, they intersect finite many points, at least they intersect in discrete number of points. Oriented. S is co-oriented. These are requirements. And if we are in this situation, then we can assign to every intersection point. And assume that we have two intersection points of opposite sides. So we can deploy here R, here is S, and here, I'm sorry, it is not interested in the dimension in these dimensions, so, but I can draw a picture. Let at least R, I will draw it. This is R, this is S, and we have two intersection points of opposite sides. Here, Q are of opposite sides. Well, also we have some restrictions. First of all, dimensional restriction. R plus S is fine. The second is not so important for us, because we will swap between R and S. So the sum is 5 and it's 3, but actually it is implemented. This is goal which is coordinated. Also, we would like that before some condition that that any loop which is homotopically trivial in the component of S, sorry, yes, is homotopically trivial in the component of E. It is for sure true if S is large in dimension. So if R is at least 3 also, then it is for sure true, but it is not required. So this is technical, I don't want to. And also, well, and also assume that we can find such two loops. This one. One in S, one in R from E to Q. So we get this such loop A. And about this A, we want that first it do not pass through other points of intersection. Maybe there are other points of intersection. So A is disjoint from the intersection with except for A and Q. And also we would like that A is homotopically trivial, contractible, homotopically trivial in B. So some technical conditions like that. In our case, it will be simple dynamic, so this will be trivial and so on. But if such conditions are satisfied, then what is weak entry? Weak entry is some special construction of isotopy. Our special construction of isotopy. We can make an isotopy. Then there exists an isotopy ambient isotopy of the whole network, which starts from identity. So we start from identity. We have from B and then isotopy. So that we start from identity. Moreover, our isotopy is trivial near all other intersection points of parameters. So H is constant near all intersection points except Q. And after this isotopy, these 2 points disappear. So if we take H1 R and intersect with S, then this is exactly all the same points instead of yes. So this trick allows us to cancel 2 intersection points by an isotopy. And under some restrictions. And how this will be used? This will be used to just the last sentence. Assume that we have Q and we have P. Again, these 2 consecutive points of gamma plus 1 and gamma. And we have here left hand sphere of Q and right hand sphere of P. And assume that this algebraic number of trajectories from P is 1 or minus 1. But the number of intersection points can be large. So we can, for instance, 100 positive trajectories and 99 negative trajectories. So that's algebraic numbers. But then we already know that performing changing present light field, we can perform any isotope. And then we'll use the symmetry to cancel under some restrictions in some situations. We will cancel all points except for one. And then we apply theorem which we have put today. If we have one projection, then we can cancel this pair. So the idea is that this Whitney field allows us to replace a very inconvenient condition that there is one projected by a convenient condition that algebraic number of projectors is one. And this is our next problem. Well, yes.
свидания.
Да, там
да, ну я вот как-то... Не, я вот понял, какой степ-бай-степ там, где мы вообще используем. Ну, то есть, как я понял, мы должны противоречить.
да.
То есть, я не знаю, где используется, что, ну, ладно, допустим, вот. То есть, можно взаимодействие, если это было стандартное, то мы, наверное, и пространство сделать чем-то
Это удар, это должен быть стандартный.
почему, если гладкая структура не стандартная, почему не пространство
Нет, она не может сделать, это вообще говоря не очевидно совершенно. Вполне могло быть, что стандартная, а гладкая структура нам нужно другую сторону. Сначала доказывать гладкость,